Hi everyone and welcome from the MaffsGuru today on this video with regards to using matrices for transformations. As if life couldn't be more exciting, now we're mixing transformations and matrices. Now, ladies and gentlemen out there watching, it is always good to see you here, but have you subscribed to my channel? Look, there are like 3.2 million people out there watching videos of people eating food. I will do that. I'll give it a go. Seriously, maths while eating food. I think we should take back the internet. Let's make maths the subject it should be. Let's get out there and spread that word. Now, if you can, literally please go out there and tell your friends to log onto my channel or load up my website, maffsguru.com. Or the very small act of you just clicking that little button that I'm highlighting over there in the corner really does mean the world to my very, very small channel. So thank you for what you can to do to help. Now, as is usual, let us recap the learning from today, which is above and being highlighted by probably a very large red arrow. It's building on from the work we've done with regards to transformations. And in this course, there is a lot on transformations, dilations, reflections, and translations. Believe it or not, we can use matrices to help us, you would argue, make things simpler. It might make things more complicated. Either way, it makes things just more food. Now, in the lessons we've done previously, as you can see above me, there is that whole idea that we can write equations that actually are nothing more than a series of dilations, reflections, and translations. So when we watch or look at an equation, if we know what bits stand for a dilation, which bits stand for a reflection, and which bits stand for a translation, then actually this half the battle. So this equation that I'm highlighting now, y equals minus 3, x minus 2 squared plus 7. I know, because of this squared here, that it's dealing with my standard parabola. So it starts off with my base graph of y equals x squared. But which part is the dilation? Well, as it turns out, that 3 is a dilation. Which way from? Well, if you remember, we can dilate from the x-axis and from the y-axis. Looks like I'm weightlifting, but just in a very small area. Anyway, so that's a dilation. So that graph would take this one here and dilate it by a factor of 3. Stretch it. What else? So that's my dilations. Are there any reflections? Well, yes. The minus sign in front of the 3 actually is a reflection. Where? Well, it reflects it that way. It reflects it in the x-axis. So having done that, I will then flip my whole graph that way. So it's 3 times bigger and it's now been flipped. Are there any more reflections? Nope. And so I'm now going to do all my translations. And if we remember, that minus 2 will move it 2 units to the right, which is that way, and 7 units up, which is 7 units up. That would give me some sort of graph that looks something like this. We would know what our turning point is, and yada, 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 yada. Nice when you can understand these things, but sometimes we'll be given translations and transformations and all sorts of things and asked to turn it from one function into the image using some pretty funky maths. But before I rush ahead, we need to talk about matrices. Now, there is a video, funny enough, in my channel somewhere on matrices, and it is pretty awesome because it explains how to multiply these things together. But first things first, when we are multiplying matrices, we have to make sure that we are doing the same order. Now, by an order, I mean this. This matrix 0, 1, 2, 3 is called a 2 by 2 matrix, or it has an order of 2 by 2. What it means by that is 2 rows by 2 columns. Now, the way I remember that is RC. Now, I'm not trying to be rude there. When I wake up first things in the morning, I am pretty arsey. But it means RC, as in rows and columns, and that's the order it always is. So this one here, if I just put 1, 2, how many rows do I have? I have 2 rows, but I have 1 column, so that'd be a 2 by 1. Now, what does this have to do with multiplying matrices? Well, we can only multiply matrices where, when we put them together, and we write underneath them their order. If these 2 values here are the same, then we can multiply matrices together. Yes? Order of these matrices is actually really, really important. If I had something like this, 1, 2, 3, 4, and 1, 2, can I multiply those 2 together? Well, we remember this is a 2 by 2. And this is how many rows has this got? 2 by 1 column. Are they the same? Yes. So my rules of multiplying matrices absolutely apply, and I can do that. If I was to swap them around and do 2, 3, 4, 5, mixing it up, this is a 2 by 1, This is a 2 by 2. Are they the same? No. So in that situation, they can't be multiplied together. Now, multiplying matrices is a bit funky. I'm going to move it over here a little bit because like FOIL, and if you remember what FOIL is, actually I'm going to make this a little bit simpler because all the examples we're going to deal with in a moment are a bit simpler. If you remember with FOIL, if I had x plus 2 multiplied by x plus 4, well, the reason we call it FOIL is first, outside, inside, last. We do it in a particular order. First times first, first times second, second times first, second times second. That's how I was taught it at school. So 1, 2, 3, 4, and let's just say that's 5 and 6 to make life, let's not make it 5 and 6. Let's make it 2 and 3. When we multiply matrices together, we multiply a row by a column. So we do row by column, row by column, row by column, and we keep going until it's all done. So in this situation, that's row 1, this is row 2, and we'll call that column 1. So we now do row 1 by column 1, R1, C1. There's an order to this. And when we multiply, we take each of the pairs of numbers, we multiply them together, and then add the result. So in this situation, that becomes 1 times 2 plus 2 times 3. There are pairs of numbers that we add together. Now I do my second row times my first column. Now if I had 2 columns, it's slightly more complicated, or there's more of it. But again, first number times first number is 3 times 2 plus 4 times 3. And then I just simplify that. So what do I have? 1 times 2 is 2, plus 6 is 8, and 6 plus 12 is 18. 6 plus 12 is in fact 18. Good. And there we go. That's my multiplication done. So that's going to build on what we're going to need a little bit later on in this lesson. So before we do that, let's look at the idea of where these matrices come from. And you're going to say, well, what do you mean matrices? You haven't even talked about them. Well, we're going to come up with a series of 2 by 2 matrices using some pretty simple mathematics. So the first thing to remember is that the image of a coordinate is given by x dash y dash. So when we transform an original coordinate, it goes from x, y to x dashed y dash. That dash just means it's an image. And remember, a graph is nothing more than a shed load of coordinates all put together. Right, so a reflection in the x-axis. If I draw a quick diagram here, and here is a coordinate, let's call it 2, 3, and I reflected in my x-axis, what's it going to become? Well, there's my x-axis, reflected in that, my x value stays the same, but my y value becomes negative. So now let's look at what happens to my point x and my point y, my x value and my y value. Well, my original x value was 2, my final y value was 2. My x dashed becomes 2, but my y dash became minus 2. So we can rewrite this and say, well, so we can say that x dashed became equal to x and y dashed was equal to the negative of y. Now, what's that got to do with the price of fish? Well, as it turns out, I can write this as something else. I can say, well, that's the same as 1x plus 0y. Now, you're like, well, why would I write that? Hold on, chicken, I'll tell you. And this one becomes 0x minus 1y. Now, when I have 2 terms and some numbers, I can re-express this as a matrix as 1, 0, 0, minus 1 times xy. Now, again, this builds on the work we've done previously in matrices, and if it's new to you, you'll do this. It's coming up to you. But I now know that a reflection in the x-axis is defined by multiplying by the matrix 1, 0, 0, minus 1. Now let's just do this dilation of factor k. Now those of you who can see behind my head, that table is what I'm working towards. But a dilation of factor k from the x-axis, so it's stretching the x-axis. So once again, here's just an example with some numbers in it, 2, 3. If I want to stretch it by, say, a factor of 3, then what's going to happen? Which is going to change, my x value or my y value? Well, if I'm stretching that way, it's not my x value. So that's now going to become 2, 9. It's been multiplied by 3. So now let's look at what happens with my x dashed and my y dash. So my x dashed and y dash, remember, are the points that happen. They're my images. So Does my x value change? Nope. So my x dashed and my x value stay the same. But what happened to my y value? Well, in this situation, it became 3y. Now, writing this again in a different way, or same way but different, I get 1 times x plus 0 times y, and that's 0 times x plus 3 times y. Now again, the reason we're writing it this way is because it helps us write this now as a matrix. That's the same as 1, 0, 0, 3 times xy. So, in this situation, to do a dilation of factor 3 away from the x-axis, I would multiply by 1, 0, 0, 3, which I could make it more formal by saying 1, 0, 0, k if I wanted to now change that scale factor from 3 to 7 to 12 or whatever else. And lo and behold, ladies and gentlemen, if I was to continue doing this, and I'm not going to because we'd be literally here all day, then we would end up with the table shown there. Now, I've taken this from the Cambridge Essentials textbook because that's the textbook I'm teaching my kids from, and actually it's an awesome summary. And it shows reflection in the x and y axis, a dilation from the x and y axis, and a reflection in the line y equals x. Something it doesn't show here is where we have translations. Now, translations are written actually as just order rows 2 by 1 matrices, which suggests here when I have an x and a y that it's going to be moved no x's that way, but it's going to be moved 3 y's up. So that's actually a vertical translation of plus 3. If I had this as minus 2, 7, for example, and what that would mean is 2 that way and 7 up. So we can combine all of these together. So how are we going to use this to actually do some maths? Well, I'm going to move my little head to the other side just so that I can sort of have the table on here just to try and illustrate it, and I'll make it a bit smaller as well. So what would the image be of that point? Well, image is asking for x dash y dash, so it's saying what is x dashed y dashed, and we can write that in terms of a matrix under a reflection in the y-axis. So I need to look up the right matrix for it, which is this one here. So I've got minus 1, 0, 0, 1 times my original point, and they gave me my point as 3, 4. Now, this is really trivial because ultimately you could just do this without doing matrices, but obviously it gets harder as the video goes on. So, multiplying this out, I can leave that table for a moment, gives me row by column. So minus 1 times 3, which gives me minus 3, plus 0 times 4, well, that just stays as minus 3, and 0 times 3 plus 1 times 4 gives me 4. And so my final coordinate is minus 3, 4. Is that what we're expecting? Well, when we multiply in the, when we reflect in the y-axis, I had my point here as 3, 4. It goes over here and becomes minus 3, 4. And so the theory works. Yay! How exciting is this? Now, when we have more than one mapping, we have to be careful because this is a bit of a trick. The theory states that when we do this, and this is an example from the Cambridge Essentials textbook again, great textbook. The theory states that when we have composite mappings, i.e. a reflection in the x-axis, followed by a dilation of factor k from the y-axis, if we want to combine those into one matrix, we actually have to do the order backwards. So rather than doing a matrix for my x-axis followed by my dilation of factor k from my y-axis, I'm actually going to do my dilation matrix first and then my reflection matrix. So my dilation matrix, going back to my document here, is k0, 0, 1, and my reflection in the x-axis gives me 1, 0, 0, minus 1. So 1, 0, 0, minus 1. So doing a little bit of matrix algebra, I get k times 1, which is k. K times 0 times 0, that one's 0. That one there is 0, and that turns out to be negative 1. So this is my composite matrix, my composite map, that's going to turn my value of xy into my value of x dash y dash. So let's just check with a diagram, because I know I've got the point 2 minus 3. Let's just draw a quick diagram here to see what should happen. So I've got the point 2 minus 3. So there's 2 minus 3. Reflection in the x-axis means it's going to move to this point here, which is going to be 2, 3. And then a dilation of factor k away from the from the y-axis means it's going to move it that way, assuming k is greater than 1. of, and it's going to move my y, it's going to change my x value. So it's going to become 2k, comma 3. So when I multiply these two matrices together, is that what I'm going to end up with? All right, well, k times 2 is 2k, and 0 times minus 3, it doesn't make any difference. And there we go. That gives me 3. And ladies and gentlemen, I was expecting the coordinate 2k, comma 3. And that's what I got. So just be careful there. I mean, ideally, you could have done 2 calculations and broken those into individual matrices. Life would have been good. Now, there are a whole range of questions in the methods exam that they can use to sort of trick you with these things. And one of them is transforming graphs. Now, there are a number of standard questions, but there are also a number of questions that are what I'm now going to call non-standard. In the last few years of the methods exam here in Australia, they've sort of thrown a little bit of a curveball. So, for example, here, they actually are combining transformation. So that t colon r squared points to maps onto r squared just means a transformation from the Cartesian plane onto the Cartesian plane. This here is matrix notation that gives us a rule. I'll explain a bit more about that in a moment. And here it says that we are going from an original graph of y equals 3 sine, open brackets 2, open brackets x plus pi and 4, to what would be the equation of my new graph if it went under this transformation? But we're dealing with circular functions. This was question 20 from the 2016 VCAR paper. Again, not a very standard question. They gave us a transformation, and again it was mapping from the Cartesian plane onto the Cartesian plane. This was the information that was given to me. Okay, so looking at that, we'll come back to it in a moment. But then it turned on to throw in integration. Now, while the question wasn't strictly integration, it was trying to combine those subject areas together. So those of you out there who believe you can just learn one subject, put it in a box and shelve it, learn another subject, put it in a box and shelve it, sadly with methods and in fact with maths you can't. But as I say here, let's not run before we can walk. Again, questions taken from the Cambridge Essential textbook, which is what I am teaching from. A transformation is defined by the matrix 1, 0, 0, 2. Find the equation of the image of the graph of a quadratic equation given by that. So first thing I'm going to do is write down that my original equation was y equals x squared plus 2x plus 3. And I want to go from that graph to its image. So I know I've got x dashed y dashed is given by my transformation matrix of 1, 0, 0, 2 times my original coordinates. Now I'm going to deal with one coordinate. I'm going to say let's have a generic coordinate of x comma y, or xy, yeah. Now I'm going to multiply this out, and what I'm going to get is I'm going to x dashed is the same as 1 times x plus 0 times y, and I get y dashed is equal to 0 times x plus 2 times y. Or, more importantly, x dashed is equal to x, and y dashed is equal to 2y. And you're going to say, well, why would I want to do this? Well, go back to my original equation. What do you notice are the letters used in it? X and y. What do you notice here? I've got an x and a y. Now what I'm trying to do is I'm going to try and change my x into an x dashed and my y into my y dashed, because I want the equation of my image. So in this situation, just rewriting that, x can be just strictly replaced for x dashed, and in this case that y is going to become a half of y dashed. Why? Just rearranging it. So now let's put this into my equation. Y became a half of y dashed, and everywhere I see an x, I can put x dashed. So that's x dashed squared plus 2 lots of x dashed plus 3. Now I don't need the dash anymore because this has now become the equation of my image, and all of my equations will always have y's and x's. So this now becomes y on 2 is equal to x squared plus 2x plus 3, or moving that 2 around we get 2x squared plus 4x plus 6. So just multiplied by 2. And ladies and gentlemen, this now is the equation of my image. Yeah, now remember, if we go back, do we recognize what that actually meant? Well, we could look it up as 1002. So 1002 would fit that there, which means I've had a dilation of factor 2 from the x-axis. So all of my y values would effectively have been doubled. And that's exactly where that equation came from. Here's another example, again from the Cambridge Essentials textbook, making it slightly smaller because it doesn't need to be that big. Now, I've got a transformation, again, mapped from the Cartesian to the Cartesian plane, given by this. Now, all it's trying to say, in its really confusing way, is that x dashed y dashed is given by 5, 0, 0, 1, xy, plus 5, 2. Now, we haven't seen it before, but I talked about it earlier. That now is a translation, yeah. So translation 5 units that way and 2 units up. So I can rewrite these equations as x dash is equal to 5x plus 5, and I can get y dash is equal to y plus 2. Now you're going to say, why am I doing that? Because, again, I want to find the image of the curve with the equation y equals 1 over x. They've given me in my original equation y equals 1 over x. How is that helpful to me? Well, because I now want to get the image. I've got to replace my y and x, and the way I'm going to do that is rearrange these two equations here. So I now know that x dashed minus 5 is 5x, so in which case x dashed minus 5 on 5 is equal to x, and I know that y dashed minus 2 is equal to y. So those are my two equations, which I'm now going to substitute back into here. So y can become y dash minus 2. Well, I don't need the dashed anymore because I've got my equation. That's what I'm building up. And this is going to become 1 over x minus 5 on 5. Well, I know that 1 over basically just makes it the reciprocal, just means it's going to flip it upside down. So rearranging this or rewriting it, I get y minus 2 is equal to 5 on x minus 5. Oh, that's not a, what am I doing? 5 on x minus 5, and then swap the 2 over, gives me 5 on x minus 5 plus 2. And there, ladies and gentlemen, is the equation of my image. Now, these are the types of questions I would expect to see in the exams, more and more so. Sadly, we've noticed that, yep, they don't do that. And here I'm going to go through the solutions of the 2017 and 2016 exam question. So, same thing. I've got a transformation. I've got a transformation matrix that says x dashed y dashed is given by 2, 0, 0, 1/3 xy. I'm going to write those out longhand so that I can say that x dashed can now be given by 2x, and I know that y dashed is given by y on 3. Why is this important to me? Because I want to know what my x and y values. Why? Because there is my equation that's got a y and an x in it. Rearranging this gives me that x is equal to x dashed on 2, and y is equal to 3y dash. So where I see a y in my equation, I'm going to put 3y dash, and where I see an x, I put x dashed over 2. So write my original equation out. Y is equal to 3 sine brackets 2 brackets x plus pi on 4, close brackets and close brackets. Let's do some substitution where I see a y. I'm going to do 3y dashed. I don't need the dashed because this is going to be the equation of my image, times 3 sine brackets 2 brackets. Where I see an x, I'm going to do x on 2 plus pi on 4 and close some brackets. Well, good news there, that 3 and that 3 cancels. And I've got y is equal to the sine of 2 lots of x on 2 plus pi on 4. Well, I'm going to take this 2, I'm going to halve. I'm going to take a half outside the fraction. That's going to give me y is equal to the sine of 2 on 2 x plus pi on 2, which means they disappear, and I get that y is equal to the sine of x plus pi on 2. I am a freaking genius. So what do I do now? I look at all of my answers for my multiple choice and notice that not one of those is my answer. Now, either I've made a mistake or they're trying to trick me. And as it turns out, they are absolutely trying to trick me, because I know that the cosine of theta is equal to the sine of theta plus pi on 2. And that's exactly what we've got here. So that can actually be rewritten as y equals cosine x, which just so happens to give me D as my answer. See how this did? That didn't just deal with transformations, it dealt with transformations and circular functions. Let's have a look at the next question. Yeah, now as I said, this is a full-on sprint. And by that I mean we're dealing with this integration notation. Now, I absolutely love that notation because what it's telling me is that I've got areas of stuff. So before I go any further, whenever I get this notation, what that's trying to tell me is that the area under a function, and I always draw these things as straight line graphs, between the limits of 0 and 3 is 5. That's exactly what that means. The area between 0 and 3 of my function is 5. It wants to know what the area of g of x is between -3 and 0. How are we going to know what that is? Well, as it turns out, function of x maps onto g of x using this thing here. Now, it's slightly different from the previous questions because I don't have any function to substitute it into. So what I now need to do is work out, well, what does that notation mean? What does -1, 0, 0, 3 mean? Where does it come from? Well, by the looks of things, there is only one, using my table here, there is only one transformation that has a -1 sign here, and that's one there. So there is, somewhere here, a reflection in my y-axis. And this 3 down here seems to be created by a dilation of factor k from my x-axis. All right, so in which case I then have a dilation of factor 3 from my x-axis. So the question is, does the order of this matter? Well, as it turns out, it actually doesn't. So what I'm saying is, here is my original function. I now need to reflect it in the y-axis. So drawing a quick sketch, reflecting it in the y-axis now gives me 0, -3, and that value there is still 5. Ooh, then I have a dilation of factor 3. So the dilation of factor 3 is now going to stretch that thing up by 3. It's going to triple that area. So actually, I'm just going to write 15 there. Is that the end? Nope, because while I've dealt with this, I then have to deal with that translation, which tells me I'm moving the whole graph up a factor of 5. Yes, so if I was to draw this, and again, probably my head's getting in the way, but let's draw it over here. If I was to cut this out and slide it up the page, hopefully it will definitely be higher. So here is my area of 15. But I've now got to take account of this area here. Well, that distance there is 5. And I know this distance here is 3. Why? Because it goes between -3 and 0. So this area here, that additional area I've now added on, is 3 times 5, which is another 15. So my total area in that function there, which just happens to be g of x, is 30. And so the correct answer to this question was 30. Now, there's a lot of stuff in here to go through, and I mean a lot of stuff. And some people find this really, really challenging. And I get it. I genuinely get it. But a lot of this is through practice. My advice is if you have a summary book or you're allowed a summary book, cut out that table and stick it in. Practice. Practice the 3 types of questions and find as many as you can. And if you can get hold of the Cambridge Essentials textbook, it's really, really good for this. But you know what? I think I'm pretty much done today. And as ever, it's really, really good for you to have watched. This video has been really, really long. But because the content is actually quite challenging, or there's a lot of it. So my apologies. If you're still watching, much respect. Now, as I said at the beginning of the video, if you can subscribe, that's brilliant. There's a subscribe button for you coming up. And if you can tell your friends and people about my channel, I would be deeply, deeply grateful. And I've got a Patreon account as well. That's a whole new discussion. Otherwise, there's a video loading for you over there. Have an awesome day, and I will look forward to seeing you in the next video. This is the MaffsGuru signing off.